All right, so now we're going to be able to invoke pi bonding into ligands. I want to remind you what a pi bond is. Remember, a pi bond is a bonding interaction in a molecular orbital in which you have two sets of lobes interacting. So, for example, the most common type of pi bond that most people think about is two side-on p orbitals, right? Where you have one lobe and one lobe and one lobe and one lobe interacting. So you have two lobes total. This is an atom one, right? And this is a p orbital on atom two. But remember, you can also have a pi bond between d orbitals and, for example, a p orbital. Okay, how would that work? That would look something like this, right? So again, it's number of lobes that are interacting. Two sets of lobes interacting. S orbitals can't form pi bonds because they only have one lobe. All right, so previously we just looked at the MO diagram for octahedral complexes where the ligands were just doing sigma bond. Some ligands, if they have unoccupied p orbitals usually, or in theory d orbitals, although that's less common, that's going to be like a metal ligand, which it's highly possible in metal clusters that exist. But most of the time we're talking about unoccupied p orbitals, okay, that can bond in the side-on way, then you will have pi bonds forming. So I drew these arrows here that kind of represent the sets of px and py orbitals on each ligand, because we're kind of saying that the z orbitals are the pz orbitals are involved in some sort of sigma bond. Okay, so these p orbitals, um, if they're occupied, okay, they can be occupied or unoccupied, okay, and still be pi bonds. If they're occupied p orbitals, such as those on halides, okay, um, they can undergo and make this sort of pi bonding. And we call that a pi donor ligand. Why? Because you have an occupied p orbital and it's giving electron density to the metal, okay, in this pi bonding way. So we call it a pi donor ligand. It's donating formally, usually this is going to be 2 electrons to the complex, okay? Although in principle it could be up to 4 because you have um, two of these occupied p orbitals, right? So if you think about the Lewis structure of like chlorine, right, in theory at least, you have one set of lone pair that could do sigma bonding, okay, those would be like in a pz orbital, and the other two sets could do pi bonding, okay, in the px and py. Alternatively, you can have unoccupied um, pi orbitals, okay, on the atomic orbitals or the molecular orbitals on ligands. These could be like pi anti-bonding molecular orbitals of carbon monoxide or cyanide. We refer back to the carbon monoxide molecular orbital diagram we went over in chapter 2. These complexes, for example, will have these sorts of pi accepting ligands. And so we have the right symmetry now, but we don't have electrons, and we have the right energy with these orbitals, but we don't have filled orbitals, okay? But so because of that, we're going to call these pi accepting ligands. And so we have a metal, okay, and the metal is going to donate electrons into that ligand in with pi bonding type of symmetry. So what we can do is now modify our molecular orbital diagram to include pi bonding. And so this is what we have. We have to come up with symmetry adapted linear combinations for the pi bonding orbitals on the ligands. And in order to do that, you basically look at how these vectors transform. And you don't have to worry about that in this class. I'm just, again, for anything with salts, these symmetry adapted linear combinations, I'm just giving you the answers of what the symmetry are. But basically, you need combinations of orbitals in here that have the right symmetry to give rise to bonding. And to have pi symmetry bonding, okay, the ligands have to have these symmetries. T1G, T2G, T1U, T2U. And you might be wondering, okay, what about, how many are there here? Well, T, remember the Molekine symbol on the character table is triply degenerate. And so this is triply degenerate, triply degenerate, triply degenerate, triply degenerate. They're all triply degenerate. We have 4 of them. So we have 12 pi bonding selves. Why do we have 12 pi bonding selves? Well, these are the px and py orbitals, and we have 6 ligands. So we have 12 px and py orbitals for an octahedral complex when we're talking about the ligands. Okay, we have 6 of the pz's, 1 pz for each of the 6 octahedral ligands that can do sigma bonding orbital. We went over that in a previous video, but just to refresh your memory, remember A is a 1-dimensional Molekine symbol, E is a 2-dimensional Molekine symbol, T is a 3-dimensional Molekine symbol. So that adds up to being equal to 6. So that's where this right side of the MO diagram comes from. Left side we talked about in the previous video. Please see section 6.9 if you're confused about where this left side energy ordering comes from. Now that you have this, we're going to have the same sort of interactions we had before, but we're going to have additional interactions. So we have this sigma bonding, the sigma bonding orbitals, right? Where are they coming from? Well, we have an A1G that's mixing with this A1G. Okay, so that's going to make a bonding interaction somewhere down here, pretty stable, and then an anti-bonding interaction. I'm not showing, these would be all 3 different energy levels, just don't have enough room to show them all. These would be 3 different energy levels. Okay, we have this EG, same symmetry, remember, can make bonding. So EG matches with this EG. I'm just Xing these out so we can keep track of these. That's going to make a bonding and anti-bonding here. Okay, and then we have a T1U and a T1U from the P that makes a bonding and an anti-bonding. All right, and so all the salts are accounted for. T2G. Last time when we didn't have pi bonding ligands, T2G remained non-bonding. It just came right across here, didn't change in energy. But now you have something with the same symmetry that you can bond with, the pi salts. So T2G and T2G. And so you're going to make a bonding T2G and an anti-bonding T2G, shown here. Okay. And then you're going to have T1U, okay, that can bond with this T1U a little bit. Now, there's some problems here because we've used this T1U up already, and we're trying to use this T1U up, and we're trying to bond with it. So this will be usually kind of weakly bonding. There might be some character in it, okay, but we can think about this for just simplicity if you want. You can think about it as non-bonding. It doesn't really matter. But anyway, so we're going to have a T1U, a T1G, and a T2U, basically that are going to be non-bonding. These are sliding over. All right. So those are just extra salts that we had. The main difference is that I really want to emphasize here is right here. Okay, that's the big difference here. That now this became a pi anti-bonding. Before it was non-bonding, this T2G, and this is affected by the ligand. And what you can notice here is that if you have a stronger pi donator, you have more of a stronger bonding interaction here. What's that going to do? That's going to bring this down. So donator, what I mean again, donator means you're donating electron density. Do that the wrong way. You're donating electron density, sorry guys, from the ligand to the metal, right? Pi donator in one of these salts. So if we're doing that and you have a strong pi donator, that means for whatever reason, well, the reason is overlap in energy and symmetry. There's good overlap in energy, okay? You are going to have a strong interaction. So stronger bonding, right? You're making a bond, a pi bond. So this pi bonding orbital, if it's stronger, it's going to get stabilized. And what's going to happen to this anti-bonding? Well, that's going to get destabilized, right? Remember, anti-bonding, the amount the anti-bonding orbital goes up, and any interaction has to be higher than the bonding orbital went down. So if this got a stronger bond, the anti-bonding has to go up. So if this goes up, guess what happens? Delta O goes down, okay? Now, pi accepting is exact opposite, right? Pi accepting is exact opposite. So what's going to happen with pi accepting? This magnitude of delta O is going to increase because this is going to go down, right? And so this now explains the spectrochemical series, okay? This is really the point that I wanted to tell you, okay? Before using crystal field theory, we couldn't explain this. Now at least qualitatively we can explain it. We're going to get a little bit more quantitative in the next few sections when we get into the angular overlap method. But right now, qualitatively, we can explain this. This is a pi accepting ligand. It has a pi star, okay, carbon monoxide has a pi star with a lot of metals that has the right energy to accept electron density from that metal. That means that it is a very strong pi acceptor, okay? That means that this, we said for pi acceptor, is the opposite trend of pi donor. This energy is going to go down of this orbital. If that orbital goes down, T2G, your T2G to EG gap increase. T2G to EG gap is your delta O. If that increases, okay, that means you're on the right side of this spectrochemical series, okay? On the other hand, iodide was one of these ones that we're talking about, like fluoride, the halides. They're pretty good pi donors, okay? And so they're doing the opposite. They're good pi donors, so they're bringing this up, this T2G up, stronger pi bonds here, bringing that level down, but importantly, moving this one up. If we move this one up, delta O goes down. So delta O goes down. Now, we can understand why iodide, since it's a pi donor, is at the beginning of the spectrochemical series. It has a lower delta O, strong pi donor. Ones in the middle, some of these in the middle are not strong pi donors or pi acceptors. They're mostly doing sigma bonding, okay, like for example, ammonia. But yeah, the key thing, crystal field theory, we couldn't rationalize this trend because crystal field theory is always talking about just electrostatics. And it didn't make sense to us before. Why do we have a negatively charged here and a neutral molecule there? If it's based on electrostatics, which is all about charge, right? The negatively charged one should have more electron-electron repulsion. Well, it's not just about electrostatics, it's also about bonding. And that's what the MO diagram embodies, okay? It takes into account not only electrostatics, but also bonding. And so hopefully now you understand the origin of the spectrochemical series, at least in a qualitative manner. To get really, really quantitative about it, you have to do the calculations, okay? And there's a little bit you can learn if you just were to write out all the MO diagrams for these different ligands. That's a lot of work, but this is indeed what people do, okay, to make these calculations and make these structural type of predictions.